Here is Prince of Persia, and here is the game, timer, level, and kid's health. Not so impressive, you might think, but what if I tell you that all this is a separate application written in C++, reading and even overwriting the memory of a different process? To make it more complicated, the Prince is running in DOSBox. Let me show you how to program something like this from scratch, so you will be able to mess with the memory of a running game. How does our C++ code actually reach into another completely separate program like DOSBox and modify its memory in the first place? Here is the fundamental problem. Modern operating systems use something called process isolation and virtual memory. When DOSBox is running, Windows creates a high security wall around it. If our C++ tool just reaches out and tries to read a memory address inside DOSBox, Windows treats it as a security threat. But Windows also provides a backdoor for developers and debuggers. To use it, we include two headers at top of our C++ file, Windows H and TLHelp32. This gives us access to the Windows API. Breaking into DOSBox or any application is a two-step process. Step 1, we have to find it. Step 2, we have to open it. To find it, we wrote a helper function getProcessID. We don't know where DOSBox is living in memory, so we ask Windows to take a picture of every single process currently running on the computer. We do this by calling create_toolhelp32 snapshot and passing the special flag. This hands us a snapshot, literally a list of every program running at that exact millisecond. Next, we set up a structure called processEntry32W and use a do-while loop with process32 first W and process32 next W to read down the list one by one. Inside the loop, we use compare to compare the name of every running executable against our target DOSBox exe. The moment we get a match, we grab its process ID. We now have the PID. We know exactly who we are targeting, but the process ID is just a name tag. It doesn't give us permission to do anything. To actually cross the barrier, we move into our main function and execute step 2, acquiring the handler. Inside main, we take our PID and feed it into the function openProcess. We have to declare our exact intentions to the operating system. We pass in these flags: process read, process write, process operation, and process query information. By passing them, we are looking the operating system dead in the eye and saying, I want to read this program's memory, I want to override this program's memory, and I want to query its internal layout. By the way, thanks for watching. This project is special because it marks video number 100 on my channel. Thanks for your support, and if you like what you see, hit the subscribe button so we meet next time. Now, somewhere inside the DOSBox memory is a tiny 2-byte integer holding the remaining minutes on the Prince of Persia level timer. How do we actually find it? If you ever used Cheat Engine, you already know the theory. We do a first scan for a known value, change the value in the game, and do a next scan to filter the results. But we aren't using Cheat Engine. We like to write our own things from scratch here. We know the game gives us exactly 60 minutes. To find it, we need to walk through the entire memory space of the running application. We set up a while loop starting at memory address 0 and walking all the way to the maximum application address. Inside this loop, we use virtual query X. We pass in our hprocess handle and ask Windows for the info on the current memory block. We can't just read everything. Some memory is reserved. Some is protected, so we write a strict if statement. If state equals commit, then we have a live readable chunk of memory. We dynamically create a vector buffer sized to fit this exact memory region, and we blast it full of data using read process memory. Now we have a chunk of DOSBox RAM sitting locally in our C++ tool. Because we are looking for a 16-bit timer, we cast this raw byte buffer into an array of 2-byte words. We run a simple for loop across the array, asking a very basic question. Does the value at this index equal 60? Every time it does, we calculate the absolute memory address by taking the region's base address and adding our index offset. But we don't just print it to the screen, we save it. We push that memory address into vector, let's call it candidate list. The first time you run this first scan, your candidate list is going to explode. You might find 10,000 different addresses, all holding the number 60. Some of them are graphics data, some are X coordinates, some are just random junk. This is where we filter. We jump back into DOSBox and wait for the timer to tick down to 59. We go back to our C++ and write a second loop. But this time, we don't need virtual query. We don't need to scan the whole game. We already have our candidate list. We iterate through that vector, and for every address inside it, we call read process memory one more time to read a single word. We check the new value. Is it 59? If it is, we keep the address in our list. If it isn't, we delete it. And you are done, you found it. You found the exact isolated memory address holding the level timer. You are thrilled. You print it and watch how it reflects real time in the game. You build a fully functional custom C++ memory scanner. You close your IDE, you shut down those books, and you go to sleep feeling like a master reverse engineer. But tomorrow, when you wake up, boot up the game and run your tool again, things do not work anymore. You get some garbage value. But let's focus on the bright side. You learned about dynamic memory allocation. Every time you launch DOSBox, Windows throws it into completely different physical location in your RAM. If you tell C++ to read memory address 1E46A000 today, tomorrow that address might belong to anything in your application memory space. This means absolute memory addresses are completely useless to us. We can't rely on where the game is loaded, but we can rely on the game's compiled machine code. The core executable segment of Prince of Persia contains static instructions that never change. We need a landmark, a signature. We need an array of bytes, the EOB anchor. To find this, we can write a quick differential analyzer. I dumped 16 kilobytes of memory just behind our temporary timer address, restarted the game, dumped it again, and compared the two files. From the shared bytes between these two dumps, to eliminate everything that might change between runs, I chose a 15-byte machine code sequence sitting right next to our target variables. No matter where Windows throws DOSBox in RAM, this exact sequence will always be there. After we grab a handle to DOSBox using OpenProcess, we need to scan the memory. We are going to use a virtual query X to query memory pages and ask Windows, hey, is this chunk of memory actually committed and it is readable? If the info state is commit and it doesn't have the no access or page guard protections, we know it's safe to read. When we find a valid block, we grab the whole chunk using read process memory and pull it into a local vector buffer. Then it's just a matter of sliding a window across that buffer. We run a simple for loop using memCompare to compare our anchor pattern against the memory chunk. We take the base address of the memory region, add our loop index, and return that absolute memory address. We now have our anchor. And here is the interesting thing. The distance between our AOB anchor and our game variables never changes. For the timer, I calculated that it sits exactly 4000 bytes away. So instead of hard-coding a fragile address, our code simply calculates the pointer dynamically. So timer minute address equals anchor points address plus timer minutes offset. It is not as bulletproof as you might think, but let's address this problem later. Now, it's time to hunt down something fun like the kid's health or the current level. You fire up your memory scanner, you find your 3 hit points, take some damage, filter for 2, and repeat. Let's write the offset down and do the same for the level. Here the situation is not that bright. Your scanner refuses to drop below 3 remaining memory addresses. Every single time they should change, all of them update in perfect synchronization. Welcome to the shadow variable trap. You have the core logic engine keeping track of the real game state, but you also have the rendering engine drawing the HUD and maybe even a completely separate audio engine. Every frame, the game might copy the real value into these shadow variables, for the UI to read, for instance. If you only modify the UI shadow variable, it might look alright, but the core engine still thinks differently. You will see this in a moment when we start to tinker with health. For now, let's upgrade our C++ scanner with a force down feature, extracting the relative offsets of our remaining candidates. Now, we know that one of these is our winner, and if we have no more data to work with, the best we can do is just test them all and see what happens. So we have our anchor, and you've cut through the shadow variables to find the master engine state. You calculate the exact distance between your anchor and your health variable. You write it into your C++ namespace as constant health char equals 3D2A for my case. You compile, restart the game, run your tool, and you get garbage. Your offset is pointing to something completely different. Wait a minute, didn't the AOB anchor fix the shifting memory problem? Yes and no. Welcome to the chaotic reality of 1990s DOS architecture. You see, when you hack modern games, you are used to flat, continuous memory layout, but those games had to survive with a strict 640 kilobyte RAM limit. A game as massive as Prince of Persia could not physically fit its entire engine, graphics, and level into memory at the same time. Developers used something called memory overlays. The game loads dynamically into temporary heap chunks. When you are on the title screen, your health variable literally doesn't exist. When you press space to load level 1, the engine backs DOS for chunk of free memory, creates the prints and drops him in. If we calculate our target addresses minus anchor address offset at the wrong time, or if the game loads a different size level, bad for us. For this use case, for our own Homebrew hacking tool, it is not a huge issue. Just remember, we cannot run our memory scanner while the game is sitting on the title screen. The memory structure hasn't been built yet. Simply try to do the same things at the same time. Even then it might fail, so be ready to close the game and run it again. Time for another cool thing. We want to press the H key, intercept the game's 16-bit integer holding our max hit points, and increase both our capacity and our current health. Prince of Persia has two health values, max health and current health. We must alter both. Let's start by setting up a standard Windows API hotkey listener inside our main while loop. We use an if statement, checking get async key state with the virtual key code for H, bitwise ended with 8000 to see if it's currently being pressed. When we detect the key press, we trigger our custom injection function. Inside that function, we read the current memory state. We calculate our absolute pointers, health address equals health current, and the same for the health max, which we discovered by scanning memory for 3, drinking a big potion and scanning for 4. When we pressed the key, it looked like nothing happened, but in fact it did. The UI just didn't update. If I force the kit to lose life, we can see that things worked. We can do the same thing for the timer. And you know what? We can do something similar for controls as well, but that will be a topic for the future. If you like tinkering with Prince of Persia, check out this video. It is such an amazing game and I will definitely continue giving it all the love and praise it deserves. I hope you learned something new. Comment, like, subscribe, or even consider becoming a member if you want to support the channel. See you next time. Ciao!